Hello class, welcome to Connected. Children, in today's chapter we will be learning about circles. Let's get into a small introduction before moving in depth of the topic. In class 9, you learned that a circle is a collection of all the points in a plane that are at a constant distance, that is radius, from a fixed point, that is center. You have also learned circle related terminology like chord, segment, sector, arc and so on. Before we move through the tangent of the circle, children, we need to have a fundamental understanding of circles. Let's look at the various scenarios that might occur when a circle and a line are shown in a plane. Let's look at the circle and a line PQ. In the visual part, there are three possibilities. First, the circle and the line PQ do not share a common point. PQ is referred as a non-intersecting line with regard to the circle in this example. Second, the line PQ and the circle both have two common points A and B. In this example, the line PQ is referred to as a secant of the circle. Third, there is only one point A that is shared by the circle and line PQ. The line is referred to as a tangent to the circle in this example. You may have seen a pulley mounted on the top of a well which is used to draw water from the well. When seen as a ray, the rope on both the sides of the pulley looks like a tangent to the circle representing the pulley. Is there any sort of other line position with regard to the circle beside the one listed above? As you can see, there is no alternative way for the line to be positioned in relation to the circle. We will look at the existence of tangents to a circle as well as some of their features in this chapter. Now children, we will go through the important parts of this chapter. Firstly, we need to study about tangent to a circle. You all saw in the last section that a tangent to a circle is a line that intersects the circle just at one point. Let us now do the following activity to comprehend the presence of a tangent to a circle at a point. Activity 1. Take a circular wire and connect it to a straight wire AB at the point P, such that it may revolve in a plane around the point P. Place the system on a table and gently spin the wire AB around the point P to get multiple straight wire locations. The wire intersects the circular wire at P and at other points, that is Q1 or Q2 or Q3, etc. at various places. You can see that it will only cross the circle at point P in one location. This demonstrates that a tangent exists at circle's point P. As you continue to rotate, you will see that all the other locations of AB will intersect the circle at P and another point such as R1 or R2 or R3 and so on. As a result, you can see that at any point of the circle there is only one tangent. You may have seen that when the position AB advances towards the position A', B', the common point, say Q1, the point AB advances towards position A', B'. The intersection of line AB and circle progressively approaches the common point P. Finally, the point P in the position of A', B' of AB corresponds with the point P in the position of A', B' or AB. What happens if AB is rotated rightwards around P once more? The common point R3 gets closer and closer to P until it finally coincides with P. The tangent to a circle is a specific distance of the secant which occurs when two endpoints of its corresponding chord meet. Children, please go through the rest of the activity on your own. If you go through any problem, please let me know. This characteristic of a tangent will be now shown. Now we will go through the theorem to prove this property of a tangent. Theorem 10.1. The tangent at any point of a circle is perpendicular to the radius through the point of contact. Proof. A circle with a center O and a tangent xy to the circle at the point P is presented. We must demonstrate that OP is parallel to XY. Join OQ with a point Q on XY other than PQ. must be located outside the circle. Can you tell me why? If Q is located inside the circle, XY becomes secant rather than a tangent to the circle. As a result, OQ is longer than the circle's radius OP. Because this occurs at every point on the line XY except on the point P, OP is the shortest of all the distances between the point O and the XY points. As a result, OP is parallel to XY. Now children, we will move to our last and second important topic of this chapter, number of tangents from a point of a circle. Let us try the following activity to estimate the number of tangents from a point of a circle. Activity 3. Make a circle on a piece of paper. Insert a point P within it. Is it possible to draw a tangent to the circle through this point? All the lines that pass through this location cross the circle in two places. As a result, no tangent to a circle can be drawn across a point within it. Next, tangent should be drawn via a point P on the circle. At such a location, you've already noticed that there's just one tangent to the circle. Finally, start at a point P outside the circle and try to draw tangents to the circle from there. What are your observations? You'll see that this point, you may draw exactly two tangents to the circle. These facts can be summarized as follows. Case 1. A tangent to a circle crossing through a point P inside the circle does not exist. Case 2. A circle has a single and a unique tangent that passes through the point of the circle. Case 3. A tangent to a circle through a point outside the circle has precisely two tangents. T1 and T2 represent the sides of the contact of tangents PT1 and PT2 respectively in figure 3. The length of the tangent from the point P to the circle is the length of the tangent segment between the exterior point P and the point of contact with the circle. PT1 and PT2 are the lengths of the tangents from P to the circle in figure 3. The lengths PT1 and PT2 share a characteristic. Are you able to locate this? PT1 and PT2 should be measured. Are these the same? This is always the case. Now children, we will go through a theorem to prove the previous slide topic. Theorem 10.2. The length of the tangents drawn from an external point to a circle are equal. Proof. A circle with a center O and a point P outside the circle and 2 points PQ and PR on the circle from P are presented. We must demonstrate that PQ is equal to PR. We combine OP, OQ and OR for this. Then angle OQP and angle ORP are the right angles because they are the angles between the radii and the tangents and they are the right angles according to Theorem 10.1. Now in the right angles OQP and ORP, OR is equal to OQ, that is the radii of the same circle. Side OP is equal to OP because common side. Therefore, triangle OQP corresponds to triangle ORP. Thus gives PQ equal to PR. It was a great experience and I'm pretty much sure that you guys feel the same. With that said, today's class comes to an end. We will meet in the next one. Thank you for learning with me.